those off today.
Okay, where were we? Okay, yeah, finishing up week 3. I put a nice snip of the board from a week ago today on LMS for you, so no excuses that you don't know what PDU means when you see it on a test. Anyway, yeah, so each layer, the bottom layers, have a protocol data unit. At the bottom it's called bit. Data link layer, it's called a frame. Network layer, it's called a packet. Session layer, it's called a segment. Oh no, I'm sorry, transport layer, it's called a segment. It's a little bit off there. Transport layer has port numbers. Network layer has IP addresses. Data link layer has MAC addresses, physical address, hardware address. They all mean the same thing. And no address at the bottom layer. Physical layer. RS-232 is at the physical layer. We did a lab with that where we connected 2 computers together, point to point, and sent some ASCII characters across. Then Thursday and Friday we did RS-485 where we have the bus. Oh, it's still hooked up. I haven't put it away yet. And we tried to communicate on a multi-access link. Everybody had to have an address. We had to have some kind of a protocol, a media access control method in order to communicate. Pure Aloha didn't work very well. You don't have to hand that in. Oh, hang on to it. Pure Aloha didn't work very well. Token passing worked pretty good. And master slave was okay, the third one, but put a lot of reliance on station number 1. Station 1 failed, then there'd be a problem. Anyway, so yeah, that's what media access control means. That's at the data link layer, more or less. Okay, and now we're into week 4. And first thing I want to do is do this little video on TCP/IP. That was the other thing about that board diagram, was the relationship between the 4-layer TCP/IP model and the 7-layer OSI model. So the bottom 2 layers are more or less covered by the bottom layer of the TCP/IP model. Yeah, it's kind of gray whether that is true. It's true, but when I show you this next video, the guy's going to say, well, the bottom layer of the TCP/IP model is, he doesn't actually make that connection like I do. So anyway, I always like to draw it like that. The bottom 2 layers are covered by this bottom layer of the TCP/IP model, and it's got a bunch of different names. Some call it the network access layer. I like the word link. I wish I could just say the link layer, because it's, as far as I'm concerned, it's your link. It's your network interface. You know, it's that Wi-Fi adapter that you plug in, or in my show and tell, you know, I show, oh, there's one right here. There's one right there. That's a wireless network card. That's like the thing that, the USB dongle that gives you Wi-Fi kind of thing, right? Yeah. The bottom 2 layers of the OSI model is done by this thing, network interface card. So that's what I say there, the NIC takes care of those bottom 2 layers. So I like that to say that's like the link layer here. So on a test, if you put link, that's fine. Network access, that's fine. Don't put network. Don't put data link. It's not. It really takes care of the bottom 2 layers. Anyway, so I'll show you this video. Professor Messer talking about the OSI or the TCP/IP model. We've got volume and everything. Let's see.
In our previous video, we talked about the OSI model, but there's another model that you should be aware of. It's the TCP/IP protocol suite. This is often called the IP suite or the IP model. And unlike the OSI model, there are only 4 layers. So it's a little bit more simplistic to take something that's in the real world and somehow have it fit into this model. Another thing that you should also keep in mind is this particular model was also built around the idea of TCP/IP, since that is the primary protocol or suite of protocols that we use to do practically everything these days.
So this is more, like the real world. There's really only 4 layers that we're interested in. The presentation layer and the session layer, those 2 up near the top of the OSI model, they're not really important. They're taken care of by the application layer, those jobs. So this is reality. The application is your application like HTTP, web. And then the transport layer has those 2 protocols, TCP or UDP. TCP is the reliable one. UDP is send and pray. And the internet layer, that's where your IP address is, the internet protocol. And then the bottom layer, there is the bottom 2 layers, that's this thing. That's like this. Yeah, so it's much easier to think about it this way. Okay.
This model fits very nicely there. So our 4 layers here are the link layer, the internet layer, the transport layer, and the application layer. Let's look to see exactly how all of these layers work together. Like the OSI model, every time you send information from one system to another, it starts at the top layer, works its way all the way down to the bottom at the physical layer. Information is sent across the network, and on the other side, the processor is reversed as information comes off the physical layer and moves all the way back up to the application layer. Well, it's very similar in the TCP/IP protocol suite as well. We have the application layer, and then everything moves down to the transport layer, the internet, and the link. And you can see as things are going across the network, if we hit a router somewhere in between, routers work at this internet layer, so all of the information is reconstructed up to that internet layer. But of course, routers really don't care what application happens to be going over them. It doesn't care if you're looking at a web page. It doesn't care if you're looking and transferring email. It has no idea if you're doing a file transfer. It can be anything inside of those packets. Routers only care about looking at things at the internet layer, and then it routes it on its way. When it finally gets to the other side, finally up at the transport layer and application layer is where these 2 stations are really talking to each other. But below those layers, everything else in between is all the networking and the routing and the switching that takes place to get information from one side of the internet to the other.
So he's talking about your, your application on one end, your web browser, and the application on the other end, the web server, talk to each other at the application layer. And also, transport layers involved in order to guarantee delivery from that side to that side. TCP says, if it didn't receive all the packets, it won't acknowledge, and eventually this side will send again. This side expects an acknowledge every time it sends packets across, and if they don't get acknowledged, they get dropped. They must have been dropped, and TCP takes care of resending the packet across. So it guarantees delivery thanks to TCP.
If we had to fill in some of those layers then, let's look to see what we might put into those particular sections. Here at the link layer, we're dealing with things at the lowest layer of this IP protocol stack. In the OSI model, the lowest layer is the physical layer that deals with signaling, but the TCP/IP model doesn't really deal with things at that level. It's really dealing with things from an IP protocol perspective. So in the link layer, we're really talking about protocols like ARP, which is more of a layer 2 if you wanted to compare this to the OSI model. ARP,
Well, we're going to be studying ARP ARP is Address Resolution Protocol. It takes care of relating the IP addresses of all the different devices that are on this network to the corresponding MAC addresses, right? You guys had to write down MAC addresses on that paper. These are all the MAC addresses of all the devices in this room, because these are all the devices that are on this subnet. And yes?
So wondering on the diagram, the switches have MAC addresses?
They do, yeah.
So, but they don't have IP address?
No. No. They only do for management purposes. Like if you were to learn about Cisco networking, you would configure a switch with an IP address so that you can manage it remotely. You can connect to it and you can telnet to it. You guys haven't done that in your Linux class yet, right? Your SSH. You're going to connect to your Linux computers from a remote computer, log into it, right? You're going to log in as root or whoever your usernames are, and manage your computer remotely. Well, you can do that with a router, you can do that with a switch, at least Cisco switches and routers. So, to answer your question, typically we say no. Switches are not interested in IP addresses at all. They only look at the Ethernet, the MAC layer, like the data link layer. They only look at this to look at the source and destination MAC addresses. They don't care about anything beyond this. They don't look at the IP address.
So it's, when you're on the internet, the routers that are doing most of the work.
They have
Define
IP
things.
address. Yes.
Switches don't really.
No.
Other than their.
They don't show up. That's right. When we're doing that trace route, you don't see switches
Yeah.
at all.
It's like they're not there.
It's like they're not there. It's like they're transparent. They actually call them transparent bridges
Do they?
because they're transparent. Yeah. There's no way to find out if there's a switch in the way. There's no way. Like at home, if you had a bunch of switches at home, there's no way to map your switches using a tool like that. Because they don't respond to the IP address at all. Only when you're talking about managing switches, you can set them up with an IP address so you can connect to them and manage them. Yeah, so we've got that switch back there that we're all wired up to, and it knows all these MAC addresses because it knows by looking at the source MAC address of every frame who's where, who's on what wire. It knows which of those blue wires is you based on your MAC address.
Or address resolution protocol, of course, is responsible for finding the MAC address of a system. So it will broadcast out that it needs to know the MAC address of a certain machine that has this IP associated with it, and that machine will hopefully respond back with its MAC address. That's the first thing that has to happen every time a system needs to communicate out on the network. So
when you guys pinged, right, last week you built that multi-network with a subnet on the left and a subnet on the right. Subnet 10 was on the left, subnet 99 was on the right, router in between. Your devices had to use ARP to learn the MAC addresses of who they were pinging. And that goes on in the background. Unless we tell Packet Tracer we want to see it, which we will be doing next week, or probably on Thursday, Friday.
address resolution protocol makes sense then that we would put it down here at the link layer. The next layer up, the internet layer, probably best correlates to layer 3 of the OSI model, because this is where you would find IPv4, this is where you would find IPv6, this is where some of the other gateway protocols might exist, and ICMP is obviously a control protocol, some management functionality.
So ICMP is the Internet Control Message Protocol. It's used to manage IP, to manage the network. It's used by ping. There's an ICMP special packet called echo request that gets sent out, and when the computer at the other end sees it, it responds with an ICMP echo reply. So the ICMP protocol is essentially the protocol that ping uses. It's also the protocol that's used by the traceroute program to see all those routers between you and the other end. That's ICMP at work.
It all happens at that layer 3 of OSI. It all happens at the internet layer of the TCP/IP protocol stack. The next layer up, transport layer, is very much like the transport layer of the OSI model, but here it is the third layer up, and obviously TCP and UDP are the workhorses of the transport layer when we're talking about the TCP/IP protocol series of protocols. The application layer then is everything else. We would have all of our applications loaded just above that, and I just put, gosh, a couple in here: FTP, BootP, SSH, IMAP, Telnet. If it's an application and it's sending data, it goes into the application layer.
So I hope you appreciate why that very first day I had you go through that exercise. For every service on the server, identify the port numbers, TCP or UDP or whatever, right? I had to get you looking at port numbers right there. So, you know, when he mentions TCP and UDP, yeah, I've seen that before. Kind of thing.
Of the TCP/IP protocol model. So you can see there are a number of differences between the OSI model and the TCP/IP protocol stack, but hopefully you can also see where the similarities are. And if we're only talking about TCP/IP and the functionality of those protocols, then it fits perfectly here. And you can start to see also why the OSI model is used in a much broader sense, because it does refer to the signaling, it does deal with things at a much lower layer, and it breaks things out a little bit more detailed all the way throughout each layer of that model. But if we're only talking about TCP/IP, this IP protocol suite is really a nice way to represent the communication all the way from the link layer all the way up to the application layer.
Yeah, he talks a little bit too much, but he's pretty good. Professor Messer. Okay, so that was that. Now, so we're into the next PowerPoint here called Devices and LANs, and it's actually called Backbone Networks in the textbook. It's chapter 15, which is quite a ways in. But really, we're talking about the lower layers for the most part. So we're going to talk about these things, which of course I'll have to show you my show and tell again. So passive and active. Passive just means you don't have to supply power. I remember in the old days there was a network called ArcNet, and it used a passive hub, just a box that you plug everything together. Most hubs are active, like this one. You need power. Bridges, switches, routers, all kinds of stuff. So this is kind of, this is that 5-layer model. So it's just like the 4-layer model, except the bottom two are combined. Right? The data link and physical layer are actually called the link layer. So each device kind of operates at different layers. The hub and the repeater. This is a hub. It's a repeater. It's just like an amplifier. It just regenerates a signal. It's down at the physical layer. Doesn't look at MAC addresses. It just connects things together. Whereas the bridge or the switch works the data link layer. So I guess that's a good reason for the author splitting the bottom two layers. So as the bridge or the switch operates at the data link layer because it looks at MAC addresses. The router works at the network layer, or the internet layer, in the TCP/IP model. So I don't have a router here, but you've used one in Packet Tracer now. These, the turquoise or greeny looking things, those are switches, and these are routers up here. Switches have lots of interfaces. The routers only have 2, maybe 3 interfaces. Our routers had 2, Fast Ethernet 0 and Fast Ethernet 1. And then we have something called a gateway, which, like in the electrical program, gateway to connect completely different types of networks together. In industry, there's a whole bunch of different network protocols, network worlds that we connect together using things called gateways. So that's why it shows the gateway covering all the layers. So a gateway is the real definition of a gateway is a device that connects dissimilar types of networks. Where nowadays, we all use TCP/IP. Even Apple uses TCP/IP. You know, Windows uses TCP/IP. Phone uses TCP/IP. So we don't really need gateways anymore. So, but in the industrial world, where we have different legacy network types, we have gateways to connect them together. So, remember when I worked at Algoma Steel back in the 80s, we had this gateway that we paid $100,000 for to connect the IBM mainframe to the DEC process control computers. It was this mysterious device to connect the different kinds of networks together. Anyway, so a repeater connects segments together. It doesn't filter. It just passes everything through. It works at the physical layer. Not much to it. So a repeater connects segments, cable segments together. That's about it. The repeater just forwards every frame, every bit. It has no filtering capability. A repeater is a regenerator. This author likes to say it's not an amplifier, but you can say it's an amplifier. I won't be bad. So it cleans up the signal, right? As the signal goes down a wire, it gets dirty, noisy. It cleans it up. So you can extend the distance of your cable by using a repeater. That's the name, repeater. And a hub is just a multi-port repeater. Like by definition, a hub, and when we're talking about this stuff, is just a multi-port repeater. This is a hub. It's also a repeater. Yeah. A bridge, though. A bridge is intelligent. It looks at the MAC addresses. So it works at layer 2, the data link layer. So for every frame that comes in, it looks at the source address and records it in a table, keeping track of which port has that MAC address. Okay, so the bridge over here, it knows that we've got last number 41 and 42 over here on port 1. So in the table, 41 and 42 are on port 1. We're over here, the last digits 12 and 13 are on port 2. So in the table, 12 and 13 are on port 2. So these guys are communicating with each other. It doesn't send the frame across. It only sends the frame across if this guy uses this guy's MAC address as a destination. Then the bridge sees it and forwards it across. So this shows how the bridge learns. Originally, when you first turn the power on, the table is empty. As computers start transmitting, it learns the MAC addresses of each device and what port they're on. So, routers. So routers connect LANs together, and they usually connect you to a WAN as well. Like at home, you have a router to connect you to your internet service provider, wide area network. The term backbone network is used, when you connect a bunch of networks together, a bunch of LANs together into a backbone. You can have different backbone topologies. So in a bus backbone, the topology of the backbone is a bus. So this would be a bus backbone. So you've got LANs connecting everybody together onto a backbone. you know, so each LAN would have clients and servers, and they'd be able to communicate within their group. And they can also communicate outside of their group if needed. Don't forget about the broadcast address. Do you remember the broadcast MAC address? You have to know what the you have to know the broadcast MAC address, and it is 1, 2, 3, 4, 5. You have to know that address. That's the only MAC address I make you memorize. The broadcast address. When a bridge sees broadcast address as the destination, what does it do? It sends it out all its ports. It forwards it to everybody. So if somebody down in this LAN down here sends a broadcast out, everybody sees it. Algoma Steel used to have this kind of a network back in the 90s when I worked there. And they used dedicated telephone lines that they rented from Bell to connect the LANs together into a switch network like this. And it was horrible. It was horrible because somebody installing a new printer driver in the office could bring down production because of excessive broadcasting. So it's a bad thing. So they switched it to a routed network where they put routers in instead of bridges and switches. And broadcasts don't go through a router. So broadcasts stop at the router. Star backbone, the topology of a backbone is a star. This is sort of what we have at Sioux College, because I often draw the college router. Like this. And I'll draw it like this, kind of looks like sunshine. And here we are down here with our switch and B1055. And here you are up in that other lab. You guys work down on the second floor of E-Wing. What's that lab? E2110? E2120? It's got a switch. E2120. And the IP address right here is, first of all, 1055. That's this room, and we are all 10.40.40. I always leave this address on the board. That's my computer's address right here. So this is 10.40.40.1. And whatever the subnet address is for E2120, it'll be .1 as well. 10 something .1. So that's a collapsed backbone in the college as far as the way the IP addressing works. So we really only have one big honkin' router here at the college that interconnects all of our networks together. So it's called a collapsed backbone. Okay, let's have a look at this hub switch router video. It's a real good one. I just found this year. I'm really happy about it. This is what
Hello, everyone.
This is what you gotta know.
We're going to talk about the difference between a hub, a switch, and a router. Now, all three of these devices are similar, but there is a difference in the way they handle data. So we'll first talk about a hub.
Good morning.
Now, the purpose of a hub is to connect all of your network devices together on an internal network. It's a device that has multiple ports that accepts Ethernet connections from network devices. Now, a hub is considered not to be intelligent because it does not filter any data or has any intelligence as to where the data is supposed to be sent. And that's because the only thing a hub knows is when a device is connected to one of its ports. So when a data packet arrives at one of the ports, it is copied to all of the other ports. So all the devices on that hub sees that data packet. So again, a data packet comes into one port, then the hub will just rebroadcast that data to every port that has a device connected to it.
So it's like a party line. Kind of like what we had here, right? Right? When one guy transmits, it goes to everybody. That's a party line. That's a multi-link, multi-point, yeah, multi-point link. So I say a hub is a physical star, right? Because it's a central point that you wire things to, but it's a logical bus, like a party line. Physical star, logical bus. Why? Because of the way it behaves.
So even if this computer here only wanted to communicate with this computer over here, these other computers would still receive the data even though the data was not intended for them. So when this happens, it not only creates security concerns, but it also creates unnecessary traffic on the network, which wastes bandwidth.
I hope that makes sense. That's why I do that lab where you have your party line. Just so you get it. Hope you get it. What a hub. Tom, make sense?
That part does.
Good.
Now, a switch is very similar to a hub. It's also a device that has multiple ports that accepts Ethernet connections from network devices. But unlike a hub, a switch is intelligent. A switch can actually learn the physical addresses of the devices that are connected to it, and it stores these physical addresses, called MAC addresses, in its table.
Do you see? The terminology is really important. Physical address, MAC address, hardware address, they all mean the same thing. The hexadecimal number. Yeah.
So when a data packet is sent to a switch, it's only directed to the intended destination port, unlike a hub, where a hub would just rebroadcast the data to every port. So as an example, if this computer here wanted to communicate with this computer over here, the data packet arrives at the switch, and then the switch will look at its table of MAC addresses and matching ports, and deliver the data to the correct port. And
So I say, we have a physical star, obviously, right? Star. It's got a central point. But it's a logical mesh where everybody's connected to everybody. And everything works great. Because the switch essentially gives you a private circuit between you and the other guy because of his MAC address. Okay? Not a party line.
then the data packet would only go to that computer. So that's the major difference between a hub and a switch. So as a result, switches are far more preferred over hubs because they reduce any unnecessary traffic on the network. So as a review, a hub only detects that a device is physically connected to it, and a switch can detect specific devices that are connected to it because it keeps a record of the MAC addresses of those devices. Now, hubs and switches are used to exchange data within a local area network. For example, such as in your home network or in a business. They are not used to exchange data outside their own network, such as out on the internet. Because to exchange or route data outside their own network to another network, such as out on the internet, a device needs to be able to read IP addresses. And hubs and switches do not read IP addresses. So that's where the router comes in. Now, a router does exactly what its name implies. A router is a device that routes or forwards data from one network to another based on their IP address. When a data packet is received from the router inspects the data's IP address and determines if the packet was meant for its own network or if it's meant for another network. If the router determines that the data packet is meant for its own network, it receives it. But if it's not meant for its own network, it sends it off to another network. So a router is essentially the gateway of a network. So here we have a private network with its router, and we'll refer to this as the red network, indicated by the red colored screens on the computers. And over here you're going to have different data packets, indicated by their different colors, which represents different IP addresses, and they are going to be entering the red network's router from the internet. Now the router is only going to accept the red data packets because they are the only ones that are intended for this network. So all of the other data packets, the yellows, blues, greens, etc., will be rejected by this router because they were not intended for this network because their IP addresses were not meant for this network. Now here is an expanded view of routers over the internet. There are 4 networks here, indicated by their different colors, and each network has their own router, along with their hubs or switches and their computers. So right now, as you can see, each network is just exchanging information within their own network. Their data is not going out on the internet, so they are not communicating with other networks. They are just exchanging data within their own network using their hub or switch. Now let's go ahead and exchange data between different networks. So let's say, for example, that this computer here on the red network wants to communicate with the computer here on the blue network. So for this to happen, the data packet has to leave their own network and go out on the internet. So the computer sends their data and it goes to the network's router. And once the data packet reaches the router will look at the IP address of the data packet and then forward the data out on the internet to the next router, and then make its way to the blue network's router, and then to the intended destination computer.
Now when he says it looks at the IP address in the data packet, which IP address? There's 2, where it's coming from and where it's going to. So it looks at the destination IP address, where it's going to. It doesn't give a hoot where it's coming from. It cares about where it's going to, so it's actually the destination IP address it's looking at.
So in a nutshell, this is how routers work. So in conclusion, hubs and switches are used to create networks, while routers are used to connect networks.
It's a great video. Really happy that that was produced. Been looking for that for years. Okay. All right. Okay. So I have mentioned logical topologies as opposed to physical. Physical is how it's wired. Logical is how it works. So recall the 4 physical topologies: bus, ring, star, and mesh. And of course hybrid, a mix of them. So those are the physical topologies that we looked at back in day 1 kind of thing. And so logical topologies describe data transmission method, not physical layout. So we have a logical bus, party line. And we can get a logical bus from a hub as well, because it just forwards everything out all ports, so it's party line. We can also have a logical ring with a physical bus, right? On Thursday, Friday, we had a logical ring, because the way we communicated was by passing a golf ball around. And it was passed around in the form of a ring. So it was a physical bus party line. And you can see it's a physical bus. The cable in front of you, the blue cable, that's a bus. There's no central controller. Just goes from device to device to device. No repeaters, no nothing. It's a physical bus. But a logical ring. Because of the way we communicated. And a switch forms a logical mesh from a physical star. We have this term called microsegmentation. Sorry about that, but that's the idea of what a switch does as part of its job. It forms logical connections between devices using that wonderful MAC address. So that's essentially what a switch does. It forms connections on the fly based on the destination MAC address. So essentially it's a logical mesh where everybody's essentially got a private circuit going to everybody else. Okay? You have to be able to describe that. There's a little video here I've got. I don't know. This is what I used to have before I had that nice video we just looked at. This one's kind of crappy.
The idea behind microsegmentation is that we get away from the shared segment and actually provide a destination before all of the traffic is visible on the network segment. In fact, in a shared segment, every single system has to look at that traffic, whether it's unicast, broadcast, or multicast.
Yeah.
With the LAN switch, we will have multiple traffic paths, or we get dedicated paths between the sender and the receiver hosts due to microsegmentation. When this computer is talking to this computer, only these two MAC addresses are being used, and therefore only those two ports are being used. So we have a dedicated conversation path. If we have a broadcast-based packet, it has to go to all of the paths.
Right. If it's got this MAC address as the destination, broadcast, it goes out all the ports. So the switch functions like a hub. Sends it out all the ports. Broadcast go to everybody.
So that it is still handled in more or less the same way as a shared segment. But the advantage is that unicast-based traffic can have separate data paths. And that's the real magic of having microsegmentation with the LAN switch.
And you need to know what unicast means. Unicast means two specific MAC addresses, a sender and a receiver. Not a broadcast. Unicast. Okay, so that's that. That's good. I guess it's not that video. Okay, all right, now we get to talk about collision domains and broadcast domains. This is kind of cool. Let's have a look and see what Professor Messer has to say about this. Hopefully.
The term collision domain is one that is relegated to the past these days. It is a historical footnote in Ethernet history. It's something you generally don't find because people are not usually connecting devices onto shared mediums any longer.
That's baloney. We use Wi-Fi all the time, and that's shared media.
Generally, everybody's directly connected to switches. Because of that, there are no longer any collision domains. The term collision also sounds really bad. Perhaps that was the wrong name to use, because in reality, collisions were something that was used in the normal process of Ethernet. It was not something you could avoid like you would avoid a collision with a car. A collision is something that would normally occur during the process of transferring information across the network.
Right? CSMACD, carrier sense, multiple access with collision detection. It was a normal thing to have collisions. Where token passing, there's no collisions.
In the old days, every device was on a big shared segment somewhere. They were all connected to a hub. And because of that, if I sent any traffic from my machine to another machine, everybody on the hub would hear that traffic. They would hear that signal coming across. This This was a lot like being on a really big conference call with many people on the conference call. The more people you get on the conference call, the more opportunities there are for two people to start talking at the same time. It's exactly the same idea when you connected so many people into that single hub. In Ethernet, obviously, just like on your conference call, only one person can talk at a time. If more than one person starts talking, you end up having a collision of information, and nobody can really understand anything that's going on. The way you accomplish this in Ethernet is through something called carrier sense multiple access. You'll almost always see this abbreviated as CSMA. This means that stations will listen for anything else going on the wire, and then they will send information across the network. The problem is when you have two stations doing this at exactly the same time, you end up having a collision. The signal itself collides, creates a conflict there, and nobody can really understand what's going on. Whenever that occurs, there is a difference in signal on the wire, and something called collision detection recognizes that these two stations have sent information at exactly the same time, and now that information is colliding. That's why we often call those older Ethernet networks CSMA/CD, because that is exactly the way they would operate. And if these stations realized that they collided with another, they would then send some extra traffic out called the jam signal that would essentially clear things out. And at that point, the stations waited for a random amount of time and tried resending the information. Obviously, using that random amount of time was important because you didn't want to, again, have another collision occur. Here's a graphical representation of one collision domain. You have one hub that's represented in the middle by this long Ethernet cable, and everybody's plugged into this Ethernet connection. And if any of these stations transmit, everybody else on this shared medium gets to hear that. Two stations that happen to communicate at exactly the same time, then you will get a collision on this network. Now, when these networks got really large, we started getting tens or even hundreds of people on a single hub. It became very, very difficult to communicate because there were so many opportunities to have that data collide right there on the network. So one of the things that we commonly did was put a bridge right in the middle. I put this representing the bridge and split the network into smaller pieces. Because the bridge was in the middle and the bridge does not pass those collisions, you can have all of these stations communicating now, and these stations on the right side, and now there's less of an opportunity for a collision to occur.
And that's what Algoma Steel did. They had a bridge that connected all the areas of the plant together using a bridge. They had steel making, iron making, coke making, administration. All those areas were connected by a bridge. But the problem was when somebody installed a new printer driver in the office, they would start sending out broadcasts trying to learn about all the HP printers on the network. And the broadcast would flood through the whole network, and that would bring down steel making and iron making just because somebody in the office installed a printer driver. It was a disaster.
Generally, we have switches these days that combine everybody into their own little segment. So we've taken that same concept of separating networks by these bridges, and what we've done is separate every single device by the bridge, and generally every single device is communicating at full duplex into the switch, which means there's one channel for send and there's one channel for receive. And because of that, you now can't have a collision. There's no physical way for this data to collide. When you're on a hub, everything is half duplex. You can't be full duplex on a hub, but in an environment like this, which is what we generally will see today, and everywhere you go is this switch right in the middle, and everybody connecting directly to that switch at full duplex.
And that's really the big difference between USB 2.0 and USB 3.0, is they went full duplex. They added extra connectors so that they have channels going both directions at the same time for your USB memory stick. So your USB memory stick, when it's copying data through, the other side's acknowledging the receipt at the same time. In the old days, it was half duplex. USB 2 was half duplex. USB 3 is full duplex.
You'll hear the term a collision domain along with broadcast domains. And although it does have a word that's similar in there, obviously the word domain is in both of those, these are very different things. A collision is dealing with the signal going across the network. Broadcasts, however, deal with certain types of packets that are going across the network. These are very important packets that are sent to every device on the network. So this broadcast is something that everybody has to know about. For instance, an ARP request is broadcast out to everybody. Hi, I'm trying to figure out the MAC address of my router. I'm going to send this out to the world. If you happen to be the router, please respond back to me with your MAC address.
So ARP probes, ARP requests are broadcast out. You can see a broadcast on a switch. You can tell because all the lights flash at once. If you're ever looking at a switch and you see all the lights flickering together, that's broadcast. So, it's kind of cool.
No other way to do this in this ARP world. You also see things like operating system notifications. They'll go out as well. A broadcast.
That's right, Microsoft will advertise server. You set up a server in Microsoft, it broadcasts out and says, "Hi, I'm a server, and here's my name, and if you want to connect to me." So it does that every 30 seconds or so.
Unlike a collision, passes right through a bridge. It goes right through a switch. And it has to. If we're directly connected to the switch, we want that broadcast to go out to everybody on that particular subnet. It stops when you hit a router.
Okay, that's critical. You have to know that. Broadcasts go through a switch. It's like Mexican food. But they stop at the router. Okay, broadcasts stop at a router. Router does not forward broadcasts. Okay.
There's broadcast IPs, all right.
There is, yeah, there's a broadcast IP, but it again stops at the router. Yeah, like 10, or how about our address here? 192.168.10.255 is the broadcast IP address for that subnet. It stops at the router. You can't send out a broadcast and send it to everybody on the internet, Tom. Sorry.
That'd be chaos.
That would be chaos. Yeah, it stops at the router.
I don't wanna imagine what kind of stuff that friend would get.
And that's the place where broadcast will not go through is anytime you hit a layer 3 device like a router on your network. Now this is a pretty important concept because just like collisions, as we put more people on the network, it became harder to communicate. As you put more devices on the network, you will see an increase in the number of broadcasts. And broadcasts are normal parts of networking. You'll see broadcasts come from different machines, for instance, when they perform an ARP request. But generally, the more devices you put on the network, the more broadcasts you're going to have. So occasionally you will want to check in and make sure you're not having too much of a problem with these broadcasts taking up too much of the bandwidth on your networks. In the picture earlier of a collision domain, I showed you this picture and said, this gets rid of collisions because everybody is directly connected to a switch. But broadcasts don't work this way. In this particular picture, everybody hears the broadcasts that are sent out. If this one machine sends out a broadcast, that switch is going to automatically copy it to everybody else who's on that particular subnet. The only time you can stop a broadcast is by putting a router right in the middle. So if this machine sends a broadcast, only the machines connected to this switch are going to see that broadcast. None of these devices will see that broadcast because there is a router right in the middle of this network.
Awesome.
Your example of Sioux College, though,
Yes.
that's a router.
Yes.
So
So
how do you
this is a
transmit-
broadcast domain, this is a broadcast domain, this is a broadcast domain, and we are in one broadcast domain.
You wanted to send something to every computer
can't.
on Sioux College.
No, you can't.
Darn.
And that's another point, Tom, is that you can't learn the MAC address of a computer in another subnet. Because ARP doesn't go through a router. ARP is how you learn the MAC address of somebody. You say, hey, who out there has the IP address 192.168.10.99? Well, your server on 10.99, 192.168, I'm sorry, 10.99, 10.254, the server. Right, remember the server 192.168.10.254? He will respond back and say, yeah, that's me, and here's my MAC address. That's ARP. Okay, so continuing on, that was the video from our collision domains and broadcast domain. So what we have to be able to do is circle the collision domains and the broadcast domains. Well, let's see, collision domains, those are made by switches. So what I'll do is I'll take this, copy it into good old Paint. I love Paint, thank God for Paint. Makes teaching so much easier. Well, unless they gave me one of those, if only I had one of those document projectors in here, I could draw on the paper, but they don't give me that, so I have to use Paint. But I can use Paint. So it says identify the collision domain, so I'll do those in red. So I'm going to pick red, and I'm going to draw circles. Ah, there we go. Okay, so, well, the switch, these wires aren't quite right. There's two separate ports in the switch. They're not both plugged into one jack. They're not plugged in like this. Right? You know what I mean? So there are two connections into the switch. So two separate ports. So the switch learns the MAC addresses of everybody over here and puts them on that port. And it learns the MAC addresses of everybody over here and thus creates two collision domains. Oh, that's not what I want. I want to draw squiggly, the freehand line. Oh, the pencil. That's how I do it. There we go. So that's a collision domain. And that's a collision domain. Because the hub's a party line. And those guys will collide with each other. But the switch isolates them. Okay, do you get it? Collision domains. Two collision domains. So every wire coming off a switch is its own collision domain. Good? Oh, and broadcast domains. Well, we do them in yellow, or whatever. So I'll pick yellow. And we got one big honkin' broadcast domain. Oh, that's a little too big. 72 points. Let's go with 36. One broadcast domain. Because when somebody sends out a broadcast, it goes to everybody. We have two collision domains, one broadcast domain. Good? Everybody able to do that? Okay, let's do this one. Identify the collision domains and broadcast domains. Okay. Let me save that. CST 104. Computer study courses, CST 104. Fall or winter 19. Domain 1. Okay, so I'll do the collision domains in red. So pick red, there's my pencil. So, collision domains. Oh. Hubs. There's no switches. So we've got one big honking collision domain. It's a party. It's one big party, right? Because hubs don't filter traffic. And same thing with broadcast domains. We got one big honking broadcast domain. So on a test, you'll be asked, how many broadcast domains are there? How many collision domains are there? So you have to understand the devices and how they work. Hub is just a party line. So, is that good? Domains 2. Oh, we got a hub and a switch. Okay, collision domains are in red, so I'll do that first. Well, we got a switch. And like I said, every wire coming out of the switch is a collision domain. So, we got 1, 2, 3, 4. You good with that? Awesome. 4 collision domains. 1 broadcast domain. So that's in yellow. Because when somebody sends out a broadcast, it goes through the switch, through the hub, and goes to everybody. So we got one broadcast domain. We don't get multiple broadcast domains until we bring in a router. Once we bring in a router, then we create multiple broadcast domains. Domains 3. Here we go. Routers connect separate networks. 1 broadcast domain per router interface. Well, so broadcast domains are in, or collision domains are in red. So looks like these guys are a bus, so they are a collision domain. They're colliding with each other. Whereas the switch, each wire coming out of the switch is a separate collision domain, right? And by definition, this is a collision domain as well. Because like I said, even though there's no devices on there other than the router and the switch, but we still say that's a collision domain. So there's 1, 2, 3, 4, 5 collision domains. How many broadcast domains? Tom? How many broadcast domains?
2.
Exactly, 2. 1 over here, and 1 over here. Because broadcasts stop at the router. So that's real important. 2 broadcast domains. And 4 collision domains. 5? 5, thank you. 1, 2, 3, 4, 5, yeah. 5 collision domains. 1, 2, 3, 4. Domains 4. Research collision domain and broadcast domain. Be able to identify each, given a diagram of the network. Oh, this is cool. Let me Google this for you. So whenever somebody asks you a question and you say, well, look it up. So let me Google that for you. It's a really cool service. I don't know if it'll work. Let's see. Oh yeah, it shows you how to use Google. You go to a web browser, type in Google, and type in whatever you want to learn about, and click search. Let me Google that for you. So if you ever have people asking you questions, and well, let me Google that for you. Real good, good term. That's it. So, what is a collision domain? There you go. Look at that. Hub. H for SW for switch, R for router, Yeah, looks like they got it right. How many are there? 1, 2, 3, 4, 5, 6 collision domains there. The hub's a party line, so they're all colliding with each other. Switch creates collision domains, and the router also. How many broadcast domains are in that diagram, Tom? 3. 3 broadcast domains. 1 here, because the router stops the broadcasts. 1 here, and 1 big honkin' broadcast domain over here, because the router stops the broadcast. So I guess the term broadcast domain and subnet go hand in hand, right? We've got, in our network, we've got, actually I think we'll take a 10-minute break. And then I'm gonna take our networks and we're gonna do an exercise